Okay, we left off at electron spin, so now we want to start with writing electron configurations. Would you find that in your notes? And as you go through this lesson, if you need to stop, have the lesson stop, then ask the sub very kindly to pause it, please. All right, electron configuration shows the distribution of electrons among orbitals in an atom, where they're located, how much energy they have. Why do we need to know that? The behavior of atoms is determined by the outer electrons, that's the bonding, and it is useful in understanding the classification of elements on the periodic table. You need to fill in your notes. I know that this word needs to go into your notes. The classification needs to go into your notes, and then the distribution up there. That was also a fill in the blank in your notes. So take a few seconds and do that. Ask the sub to pause if you need to. When writing electron configurations, there are 3 rules you must follow, and you have to know them because they will be on the test. The off-valve principle, the Pauli exclusion principle, and Hund's rule. Nothing to fill in your notes on these. I'm going to go through the rules with you and the principles with you and try to make sure that hopefully you understand. Okay, the off-valve principle. Electrons are added one at a time to the lowest energy level until all the electrons of the atom have been accounted for. All right, so let's talk about that. The lowest energy level is the first. It has an S orbital, so I'm going to fill that up first. Then I'm going to go to energy level 2. It has an S orbital and a P. So now remember here the S orbital can take 2 electrons. This S orbital can take 2 electrons. This P orbital has 3 sublevels. So I can put 1 electron in each of them and then come back and fill up for a total of 6 electrons. 3 sublevels. Each of them holds 2 electrons, so 3 times 2 is where I'm getting that 6. On a second energy level, I have now placed 8 electrons. Then I can do the third energy level. The third energy level has S's, P's, and D's. Okay? So we're going to work with that to help us fill those or build our electron configurations. Okay. You have this diagram on your paper. Go ahead and draw those arrows. Draw them carefully and accurately. You have got to know this. Notice that when it was done, this is just a column of 1 through 7 S's. Column starting at 2 and going through 7 P's. Why does it start at 2 rather than 1? Because the 1 doesn't have a P orbital. The third starts with D. Why? Because there's a D in that third energy level that's not in the first or second. So 3D through 7D. Notice that this one starts with 4F. Why? Because on the 4th energy level there is a F orbital that doesn't appear before that. All right, you've got to know that. If you don't like that way of doing it, here's a different way. Start here, 2S, enter 2P, 3S, 3P, 4S, 3D, 4P, 5S, and so on. So if you want to have that in your notes, I'm sure the sub will pause and let you put it in your notes. Doesn't matter to me how you do it, just make sure you can do it correctly, is all I need. So have the sub pause if you want to. Okay, I believe that I had you do this on your periodic table, S's, P's, D's, and F's, and now hopefully you begin to see why. Because if you know how to use your periodic table, it will help you with the little chart that I just showed you with the arrows on it. But you have to know where they're located on your periodic table. Okay. If you notice, you are filling across the rows of the periodic table. All right. So if you bring the inner transition or rare earth metals back up into the table, then the orbitals fill in order going across the periodic table. That makes a lot of sense. So here's your order. Would you stop and write this down? I know there's no place in your notes for it, but do it. Write all of this information. The sub will pause and let you fill it in. I want you to have every bit of this in your little sheet of notes. Okay, so that's what we're talking about. If you see how this is set up, you can see then that everything fills according to that Aufbau's principle. 1, 1. 2's fill, 3s, 3p, 4s, 3d, 4p. Okay, so we got through 4p. Now we scoot down and we go to 5s, and then 4d, and then 5p, and we scoot down to 6s, 4f, and we just keep doing that, just like this order shows here. Okay, so we got through that slide. Let's move on. Okay, the Pauli exclusion principle. Again, look in your notes. I believe you're going to flip the page. And what the Pauli exclusion principle says is that an orbital can hold a maximum of 2 electrons. In order to be in the same slot, they have to be opposite spins. And they can be either paired, meaning there are 2 of them, or unpaired, meaning that there is only 1 of them. But you can never place more than 2 electrons in the orbital. Hund's rule says that electrons occupy equal energy orbitals so that a maximum number of unpaired electrons results. So they need to occupy equal energy orbitals. In a sublevel, you will place 1 electron in each orbital first, then go back and pair them up. And so we have some examples for you. All right, we're not at the example, so we're going to summarize. Aufbau, electrons enter orbitals of lower energy first. Pauli exclusion, an atomic orbital can contain at most 2 electrons, and they must have opposite spins. When electrons occupy orbitals of equal energy, 1 electron enters each orbital until all orbitals contain 1 electron with parallel spins. Second electrons are added and are paired so that each orbital contains 2 electrons with opposite spins. So we'll show you what those mean, because it's not very hard at all. All right, so here's what we have. We know we're going to do hydrogen. Hydrogen has 1 electron. How do I know? I used my periodic table. That's how I knew. So you might as well get your periodic table out now. The sub will pause so you can get them out. And so hydrogen, there's its 1 electron. That's all it has, so that's all I can do there. Helium, however, has 2 electrons. How do I know? It's number 2 on the periodic table. So there's my helium. My oxygen has 8 electrons because it's number 8 on the periodic table, so I'm going to place the first 2 in the S, and then I'm going to put 1 in the second S, fill that S up. Then I'm going to put 1 in the first P, 1 in the next P, 1 in the next P. So far I have 7 electrons. I need to get number 8, and it's going to go right here. Go back to that first grouping and fill that one up. Opposite spin. If you count them, there's 2, 4, 6, 7, 8. So I know that I've done that correctly. My sodium, I fill up the S, the very first S, 1S. There's 2 of them. Sodium has 11. So I now place the 3rd electron and the 4th electron. Then I go and fill the P's, the 2 P's, one at a time. That one. And to me, this is like filling hotel rooms. Think about, you want to be by yourself and not get a roommate until you absolutely have to. So there's your roommate. There's the roommate for the next one. The next one. So far it looks like I have 2, 4, 6, 8, 10. I need 1 more, and it's going to go to the 3S. Now I'm going to go back and write my electron configurations. So in your notes, I would put that out to the side of where hydrogen and helium and sodium and titanium, I don't know about that one, we'll come back to it. So there's my helium, my oxygen, 1s2, 2s2, 2p4, because I have 8, and those, that 2, the superscripts 2, 2, and 4 add up to 8. I don't call that s squared because it's not. It just means there's 2 electrons in that first s orbital. Sodium, we just drew that one out. Remember, we had 1 in the 3s. We haven't done titanium. But if you look at the periodic table and you follow those arrows that we were teaching you about, you can tell that you have 1s2, 2s2, 2p6. So now my 1s and 2s are filled. Let me go to my 3s2, my 3p6, go back down to 4s2, and then 3d2. I know this one only has 2. I can check because if I look at it, there's 2 electrons, 4, 10, 12, 18, 20, 22. What's the number of titanium on the periodic table? 22. So I know I have 22 electrons, and I believe that they are placed correctly using those arrows to help me place them. So let me show you what I'm talking about there. If I make my arrow configuration, 1s, 2s, 3, 4s, 5s, 6s, and 7s, and then I do my p's, 2p, 3p, 4p, 5p, 6p, and 7p. Oops. And then I do my 3d, 4d, 5d, 6d, and 7d. And then I could go ahead and do my p and my f's. I won't use them. 4f, 5f, 6f, and 7f. Now, I only need to place 22 electrons. So here's my first 2. Here's my next 2. Here's my next 6. My next 3s, 3p6, and then I go to 4s next, and then back up to 3d. Because remember, I'm following that order. And I only needed 2 there, so that's my 22 electrons. All right. All right, now let's look at some ions, and those would be elements that either gain or lose electrons. So if I look at sodium, sodium is, we just did this one, 1s2, 2s2, 2p6, 3s1, but sodium is willing to give away 1 electron and become, so that one goes away, and all I'm left with is that right there. So my sodium ion has a +1 charge. That means it's missing 1 electron. It should have 11. It's missing 1, so that means it has 10. If I check, 2 and 2 is 4, and 6 more is 10, so I know that's correct. Aluminum should have 13. If you look at the periodic table, it's number 13, so it has 13 electrons, but 3 of them are gone, so it needs to have 10. So I'm going to write it down, and I'm going to take away the ones that aren't there. So that one, that one, that one, that one, and that one. That's what it looks like. I know I need to give up 3 electrons, so that takes away 1, and there's 2 more here, so that's 3. So all I have left is that one right there. Oxygen is going to gain 2 electrons, so instead of having 8, it's going to have 10. So 1s2, 2s2, those don't change, but my 2 electrons can go right here and make that become a 2p6. Okay? Now I'm going to fill in my little chart just like you have on your notes. There's the electron I'm going to lose. Aluminum, I should lose 3 electrons. Those are gone. Oxygen, I'm going to gain 2 electrons. Okay. Now what happens here is they become stable elements, or stable ions, because they have full orbitals. So let's see if that makes sense. Full, full, completely full. Had an extra. That was easy to get rid of, so when I got rid of that one, all of these are full. Aluminum, everybody's full. That one was full, and that one, I'm going to lose 3 of those. Because if you look at this, these are on the third energy level. If I can get rid of those, I'll be much more stable here. Same thing with oxygen here. I had 1s was full, 2s was full. This 2p was full, this one had 1, this one had 1, so it was easy to pick up 2 more and put them in there so that I became completely full. All right, now I want to write their electron configuration. So that one becomes 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, and then this one picked up 2 electrons, so it becomes the same electron configuration. So put those in your notes out there to the side of your little ion examples. That would be good. Now, of course, in chemistry, there are always exceptions. There are 2 exceptions. You must know these 2 exceptions, and I will show you copper and chromium. The 1s's fill, the 2s's fill, the p's, and then the 3s's, 3p, 4s, and then the d's. Now, there are 9 of those there. To have this filled, I want to have 10. So what happens is this electron in the very farthest energy level moves out and completely fills this one so that I have a more stable configuration for copper. Chromium, very similar. That one completely goes away. And I now have a more stable ion because the electrons are in a lower energy level. And this one's half full, and this one's half full, and everybody's happy. This one is completely full, this one's half full, everybody is completely happy. You must know those exceptions. Memorize them, you have to. Okay, write the orbital diagram and electron configuration for nickel. So take some time and practice that. I'm going to ask the sub to pause right here, and then you're going to have an opportunity to practice and compare your answer to what the correct answer is. So check your work. Okay, the noble gas configuration is the process of shortening an element's electron configuration to the noble gas before the element and adding the remaining electrons to it. Calcium would take a long time to write, and it does take a long time to write, but I know that from here to here is the same thing as argon. How do I know that? I look at my periodic table. I look at calcium being number 19. The element right before it is argon, which is a noble gas, so I write down in brackets the symbol of the noble gas right before the element I'm interested in, and then I fill in 4s2 for my calcium. Just makes it a lot easier. All right. So why do some elements want to lose electrons and some want to gain? Everybody's trying to get a full energy level. That makes them more stable. Which electrons can an element gain or lose? Only the outermost electrons, called the valence electrons, and those are the electrons in the outermost unfilled energy level, and they're the only electrons available for bonding. So I'm going to ask the sub to pause and let you look at, fill in the rest of your notes. How do we know which elements want to lose electrons and which want to gain? We want to follow the octet rule. Okay, the octet rule states that an element would like to have 8 electrons in the outermost energy level. Some exceptions would be hydrogen, helium, lithium, beryllium, and boron, because this one starts at 1 and this one only gets up to 5. Okay, so all the rest of the elements either gain or lose electrons to reach the closest full energy level. Most metals would want to lose electrons to return to the previous noble gas configuration. We call those cations. Most nonmetals want to gain to get to the next highest noble gas configuration, and we call those anions. Okay, so take some time and copy that. I'm going to ask the sub to pause. Would you copy that, please? All right. So before we do that, I want you to pull out your colored periodic table, and I want you to add some things on there. Let me show you what I want you to add to your periodic table. Okay, above group 1A. I want you to put the +1 because everybody in group 1A has an ionic charge of +1. Group 2A, right above group 2A, put a +2. Group 3A, that should be where boron is, +3. Now remember, boron is an exception. Group 4A, that's the carbon family, and it's going to be ±4. Group 5A, that's the nitrogen family, and it's going to be -3. Group 6A, -2. Group 7A is a -1, and then group 8A, material noble gases, don't react much at all because they already have 8 electrons, so they have no charge. Okay? Now if you look at this, you ever forget, you can kind of make it work real easily. If I want to, group 1A wants to get back to a filled outer level, it needs to lose 1 electron, so it has +1 charge. It needs to lose 2 electrons to be stable. It needs to lose 3. 4A can gain or lose, depends on who it wants to partner up with. If this is 5A, it's got to pick up 3 more to get to 8. 6A has to pick up 2 more to get to 8. 7A has to pick up 1 more to get to 8. And then group 8A already has them all, so it's not going to ever have a charge. So again, pause, add this to your notes. All right. And then we're going to move through the rest of the PowerPoint. Okay. So if you look at hydrogen, and I'm filling in the last page of my notes. Hydrogen, there it is, helium, 1s2. It has a full outer level because that's all it can take. It's a noble gas. Lithium, 1s2, 2s1, 3 electrons, so fill up the S, the 1s, and then put 1 more in 2s. Beryllium is going to pick up an additional 1. Boron, carbon, nitrogen, oxygen, fluorine, and then finally I'm back to neon. Now if I look at these, if I just looked at making the little blank with the arrow, that's what my hydrogen would look like. My helium would be that one and that one in opposite directions, so that's completely full. Lithium has 1s, which has an up and a down in it, and then 1 extra electron to go into the 2s. Beryllium has 1s, completely full, 2s, completely full. So now boron has to go into the P sublevel, so there's its 1s, there's its 2s, it has 1 electron for those 3 P's, it has 1 electron. Carbon has 1s, completely full, 2s, completely full. Now I'll start filling my P's. So I'm going to put 1 here and 1 here. If I can get my pins right. Okay. Nitrogen is going to look very similar to this. Here's my 1s. Here's my 2s. Here's my beginning to fill 2p. So I'm going to go here and here. So that's 6. I need 1 more for my 7th one. So that's what it looks like. This is halfway full. Oxygen is going to be the same situation. 1s, 2s, dealt with 4 electrons. 2p has the X, Y, and Z sublevel, so there's that one, and that one. I've used 7 electrons. Now I need to put in that 8th one. And it goes right there. All right, let's look at fluorine. 1s, 2s, 3 sublevels on the 2p. So there's a filled up 1s, a filled up 2s, electron, electron, electron. So that's what, 7 so far. Here's the 8th one. And looks like I need a 9th one. Okay. Now I want to do neon, so I'm going to get rid of this one over here. Hopefully erase it rather than scribble on it. So neon is going to be 1s. All right, so there's 1s, there's 2s, my 2 p's. I'm going to put one there, another one there. So now I have placed 7 electrons. Here's number 8, here's number 9, here's number 10. So I can write that as 1s2, 2s has 2, and then 2p has 6. So there's my configuration. Everybody's completely full, and my noble gas is very stable and unreactive. Okay, now the sub has some exercises for you, I believe, but let me go back and make sure I've got all your notes done. More appears. So let's see what we have here. Okay, so there's my valence electrons. Okay, those are the valence. Those are the ones that are available for bonding. Okay, that one can get thrown out easily, not so easily. A little changes as you go through there. I'm not worried about that yet. We'll get there. Okay, this is what I wanted you to do to your periodic table. Above these, 1A, plus 1, plus 2, plus 3, plus or minus 4, minus 3, minus 2, minus 1, 0. And then this changes. That's why they're called the transition modes, because they change. All right, we are done. And I believe the sub has some stuff for you, so I'm going to stop this and get you going on that next exercise.